Hello, and welcome to the lecture on 2.1. Today we're going to talk about functions. Let's start with the definition. A function f is a rule that assigns to each element x in a set D exactly one element called f in the set R. Now, functions surround us everywhere. Everywhere. Functions are everywhere. Let me give you a couple of examples of some functions. We have the temperature throughout the day, population of a species, elevation. These are a few examples. Let's continue with some definitions here. The symbol f of x is read f of x or f at x and is called the value of f at x or the image of x under f. And we'll get into why this is in a second, but let me finish out some definitions. The set D is called the domain of the function. The range of f is the set of all possible values of f of x as x varies throughout the domain. That is, R is equal to range of f, which is equal to the set f of x, such that x is an element of the domain D. Here, the domain is just the values that x can be, that x is allowed to be according to the function. We'll talk about this some more in a bit. The range is the image after x. So if we take an x value from the domain and we plug it into a function f, that f will do something to it and then output another value. That value that it outputs is in the range. The independent variable is the symbol that represents an arbitrary number in the domain. The symbol that represents a number in the range of f is called a dependent variable. When we think about functions, there's a few ways to actually picture them. There's 4 ways in particular. One way is with an image like this, where you have this box, and this box is doing something to an input variable x, and then it outputs something f of x. Think of it like you have something that you're intaking, you're processing it, and then you output something. For instance, a printer will intake a digital copy of something that you want printed. It will do something, namely that it types everything out on a page, and then it outputs the printed copy. That would be a function. A blender, drop a banana in, and it blends it all up, chops it all up, and then it outputs banana mush. These are all different types of functions. We are more interested, because, being in math and all, we're more interested in functions that change numbers around. So we have an input number. Our function's going to do something to that number. It's going to manipulate it in some way, and then it outputs another number. Another way to think about this is a diagram that looks like this, where we have our domain, our function, and our range. And then each element in the domain, now there's generally infinitely many elements in the domain. I'm only drawing 3 because I don't want to be here literally forever drawing pictures. And we get an input variable x. We get an input number x will map to an output number in the range of f. So we have domain variables that will output to range variables. A lot of times, each unique element in the domain will map to unique elements in the range, and we'll talk about those. It's a special type of function. We'll talk about those later. But also a lot of times, you'll have unique elements in your domain that map to sometimes the same element in the range, and that's okay. That's okay. The problem is when we have something like this, where you have an element in the domain that maps to 2 separate elements in the range. So if we go back to the previous way of thinking about it, what this would be saying is if we took a variable or we took something and we input it for processing, this processor wouldn't know how to process that thing. Would it output this value or would it output this value? It would be trying to output multiple values, so it doesn't really know what it's doing, type of thing. Now this diagram is a function. This diagram is not a function. And we can see that it's not a function by going back to the definition of what a function is. A function f is the rule that assigns to each element x in a set D exactly one element called f of x in the set R. So each element in D can only be assigned one element in R, but this element here is being assigned two elements in R. So this is not a function because it does not fit the definition of a function. Let's do an example here. Say that we have the function f of x is equal to x squared plus 2x plus 1. I want you to find the following values. A, f of 3. B, find f of 5. C, find f of a. F of 3, we have f of x here. Remember, x holds the place of a number in the domain. What we're saying here is that x is holding the place of 3. And we want to evaluate the function when the domain value is 3. So we want the range value if we have a domain value 3. Now this over here is the rule of the function f. We'll take our domain element here, square it, add that to 2 times the domain element, and then add 1. So our domain element being 3, we would get the following. 3 squared plus 2 times 3 plus 1. This. And all we have to do is evaluate now. 3 squared is 9, 2 times 3 is 6, and plus 1. So we have 9 plus 6 plus 1 will give us 16. Part B, f of 5. Now I've changed my domain element to be 5, and I want the range element that's associated with the domain element 5. So we take our 5, we square it, we add it to 2 times 5, and then we add 1, coming from this function here. 5 squared is 25, 2 times 5 is 10, plus 1. And this gives us 36. Now part C, we have domain element A, where A is an arbitrary number. It's very much like x. It's just holding the place of something. F of A will be, we take our domain element A, we square it, we add that to 2 times the domain element A, and then add 1. So it'll be A squared plus 2A plus 1. But I want you to try one now. If f of x is equal to 1 minus x squared, I want you to find A, f of 0, B, f of square root 2, and C, f of a squared. We're going to get into another type of function here, a piecewise defined function. Now, piecewise defined functions are a bit tricky. Whenever we have a piecewise defined function, we're going to give multiple parts to the function. So you'll have f of x as a function is equal to maybe g1 of x here, g2 of x, g3 of x, and so on. And this could go on for as many as we need. Now with each of these g functions, there will be conditions that x needs to meet in order to use that function. Maybe x needs to be less than -2 for the first one. And then x needs to be between -2 and 0 for the second one. And then x needs to be between 0 and 4, or something like this. These types of conditions on x for these functions. Let me give you an example of what I mean here, because this is a bit of a challenging topic. for a lot of students. But I think it's best shown in examples. Suppose we have the function f of x is equal to x squared plus 1 when x is less than 0, and 1 minus x squared when x is greater than or equal to 0. So here, x squared plus 1 would be like our g1 function. X is less than 0 is the condition, the first condition on x. What we're saying here is that when x is less than 0, we use this function. When x is greater than or equal to 0, we use this function. So if I'm to look for f of negative 1, f of 0, and f of 1, I need to figure out which function I'm going to use. So here, x, of course, would be replaced by negative 1. So x here would be replaced by negative 1 as well. We want to start by looking at the condition. Is negative 1 less than 0? Yes, so we use this function. So f of negative 1 will become negative 1 squared plus 1 because I'm plugging x into this function, my x being negative 1. Now you just resolve and you get 2. Now I have f of 0. So is 0 strictly less than 0? No. 0 is equal to 0. Is 0 greater than or equal to 0? Yes, it's equal to 0. So we use this function here. So if x is 0, then we plug it into this function, or our f function. So we would get 1 minus 0 squared, which is equal to 1. Then we check 1. If our x is equal to 1, we check is 1 less than 0? No. Is 1 greater than or equal to 0? Yes, so we use this function. And we get 1 minus 1 squared, which is equal to 0. We'll do some more with piecewise defined functions when we get to graphing, but hopefully this gives you an idea of how to find values using a piecewise defined function. The net change in the value of a function f as the input changes from a to b, where a is less than or equal to b, is f of b minus f of a. Now what we're saying here is that the output will change as our input changes. Remember, our variable for a function f of x is x. We have a variable in the domain. Now this variable is moving its way through the domain. So as our x changes from one number to another number, the output will also change. That's what we're talking about here, the net change. How far does the output change when our input changes from A to B? And that ends up being just f of b minus f of a. You just subtract the outputs. Suppose that we have something that looks like this. Now, we're not going to get into graphing in this section, but we will talk about it in another section. So we have a point here and a point here. Let's say that our function looks like this. The graph of our function looks like this. So as our x values change from a to b, the net change will be this change here. How far did my function move vertically as my input variable moved horizontally? This curve describes the relationship between the input and output variable, or the independent variable and the dependent variable. We'll talk about that more when we get into graphing. Find the net change on the interval 1, 4 if f of x is equal to x squared plus 2x plus 1. So here, what we want to do is plug in our b value to our function and our a value to our function, and then subtract. So we're looking for f of b minus f of a, where our a and our b are 1 and 4 respectively. So what we want to figure out is f of 4 minus f of 1. Now, in order to actually do this calculation, I need to know what f of 4 is. So we figure out what f of 4 is. So we plug in 4 to this function, and we get 4 squared plus 2 times 4 plus 1. 4 squared is 16. 2 times 4 is 8. So we end up with 16 plus 8 plus 1, and that will be 25. We also need to know what f of 1 is. So we do the same thing. If 1 is replacing our x, then we need to replace x's with 1. So we do 1 squared plus 2 times 1 plus 1. And we get 4. 1 plus 2 plus 1. Now we try to find our net change. That'll be 25 minus 4. F of 4 minus f of 1 is equal to their respective values, 25 and 4. So 25 minus 4 is equal to 21. And that will be the net change in the function on the interval from 1 to 4. I want to do one more example here before we get into the next topic. I think introducing this example is very important. If f of x is equal to x squared plus 2, I want you to find a, f of a, b, f of 2, c, f of a plus h, and d, f of a plus h minus f of a divided by h. Now this last one is a bit tricky, so I'm going to walk you through that one a little bit slowly. These other ones we've already been doing. C might be a bit tricky because it's a plus h, that's replacing x. But part A is pretty straightforward. F of a means that a is replacing x, so we replace x with a. We get a squared plus 2. Now I'm going to star this one because we're going to come back to it. B, f of 2, we should all be able to do this by now. X is being replaced with 2, so we replace x with 2. 2 squared plus 2 is going to be 6. 2 squared is 4. 4 plus 2 is 6. Now C is a bit tricky. F of a plus h. So I need to make a note here. A plus h is a quantity that is replacing x. So a plus h stands for a number because a and h are both numbers. So this number, a plus h, is replacing x. So we replace x with the entire a plus h. A lot of students mess this up, so be careful. We end up with a plus h, quantity squared, plus 2. Right? Now, if we FOIL this out, we end up with a squared plus 2ah plus h squared plus 2, like this. And this will become important in part D, which is why I squared it out. If you're only looking for a plus h, leave it like this. Now, f of a plus h minus f of a all over h, we need a few parts. Namely, we need f of a plus h, we need f of a, and then h is just a number by itself. So, we have f of a plus h, which is a squared plus 2ah plus h squared plus 2. And we have f of a, which is a squared plus 2. So these are our two different parts that we need for part D. So we do f of a plus h, which will be a squared plus 2ah plus h squared. F of a plus h minus f of a all over h will equal a squared plus 2ah plus h squared plus 2 minus f of a, which is a squared plus 2, all divided by h. Now notice here, we have to distribute this negative. So we end up with a squared plus 2ah plus h squared plus 2 minus a squared minus 2, all over h. Now, I want you to notice that everything without an h will cancel. A squared minus a squared, 2 minus 2. So we get cancellation here, and we get cancellation here. Everything in the numerator has an h. That won't always be the case. Sometimes you'll need to manipulate things a little bit further, but that will be taken at another time. For this section, it suffices to show this. Now what I'm going to do in the numerator is factor an h out, and we're left with 2a plus h, all divided by h. Now why did I factor an h out? Because now I can cancel my h with my other h. We're both multiplying the numerator, the entire numerator by h, and dividing the numerator by h. So we get a cancellation here because multiplication and division are inverse operations. And we're just left with 2a plus h, and that's it. So this entire formula reduces to 2a plus h. And the next topic that I want to talk about is finding the domain. How do we find the domain of a function? Well, as I've noted before, when we are looking for the domain of a function, we're looking for which values the function cannot take. When finding the domain of a function, we want to find the values the function can't take as input. And this happens because the output would be undefined in some way. So let's make another note and express the ways that for which a function is undefined. We can't divide by 0, and we can't take the even root of a negative number. Now these are the two that we know of so far. As we move forward in the class, we'll talk about other functions and their domains, and then we'll add to this list. But for right now, these are the two that we know. Let's do an example here. Find the domain of a, f of x is equal to the square root of x minus 1 times x minus 2, and b, 1 divided by x plus 1 times x plus 3 is equal to g of x. So let's start with the domain of f of x. We'll get to part b in a second. These are two separate problems, by the way, not so that we're not confused. We know that we cannot take the square root of a negative number because we have an even root here. If this was a cube root, it would be fine. All real numbers, no problem. But because we have a square root and 2 is an even number, we cannot have a negative number as a radicand. We need to find the values for which x minus 1 times x minus 2 is greater than or equal to 0. We can take the square root of 0, but we cannot take the square root of a negative number. So our problem reduces to x minus 1 times x minus 2 is greater than or equal to 0. This is going to be our domain. Whenever this product is positive or equal to 0, it's within our domain. So this problem reduces to a chapter 1 problem. We look for the values for which x minus 1 and x minus 2 are equal to 0 so that we can divide up our region. And that happens at x equals 1 and x equals 2. So now our number line is divided into 3 regions. Left of 1, which is less than 1, between 1 and 2, and greater than 2. Then we need to make our chart so that we can figure out when the product is greater than or equal to 0. So we have x minus 1 here, x minus 2, and the product x minus 1 times x minus 2. And then we divide up our region into 3 regions. Specifically, x is less than 1, x is between 1 and 2, and x is greater than 2. Now we use test points on each region. So we pick a number in the region less than 1, and we use it as a test point. So we'll start with 0. Plug in 0, we get a negative. Plug in 0, we get a negative. And then x minus 1 times x minus 2 will be a negative times a negative, which gives us a positive. Then between 1 and 2, we can use the test point 1.5. 1.5 minus 1 is positive. It's a positive 0.5. 1.5 minus 2 is negative. Negative 0.5. And then the product will be a positive times a negative, which is negative. Now remember, the radicand cannot be negative. We always want to keep this in mind when we're doing our problem. We want to keep the end goal in mind. Our end goal is to find the domain, and the radicand cannot be negative in the domain because we have a square root. Now here, this product is negative. So this region will not be in the domain. Just keep that in mind. And then we check when x is greater than 2. We can pick any number that's greater than 2. I'm going to choose 1,000. 1,000 minus 1 is very clearly positive. 1,000 minus 2 is also very clearly positive. And then we have a positive times a positive that gives us a positive. So in this region, we're okay as well because it satisfies this inequality. The product is greater than or equal to 0. So we have the region left of 1 and the region to the right of 2. That can be in our domain. Our domain is then negative infinity to 1, and we include 1 because we can be equal to 0, union with 2 to infinity. And again, we can include 2 because the radicand can be 0. If we plug in 2, we get 0. The square root of 0 is 0. And that's that part A problem. Now part B is a little bit easier. What we're going to do here is we're going to look for the values for which this function is undefined. Now, where is this function undefined? Well, we can't divide by 0, so all we need to do is set x plus 1 equal to 0 and x plus 3 equal to 0 so that we can exclude those x values. So here we're looking for the values for which x cannot be. Subtract the 1 over, we get x is equal to negative 1, and we get x is equal to negative 3 for the second one. So if x is equal to negative 1, and if x is equal to negative 3, then we get a 0 in the denominator, which we can't have. So our domain is x is not equal to negative 1 and not equal to negative 3. But if we wanted to write this in interval notation, it would look like this. Negative infinity to negative 1, union, negative 1 to negative 3, union, negative 3 to infinity. Now all I'm doing is excluding negative 1 and negative 3. Notice that we have a parenthesis, meaning that we go up to, but we do not include negative 1. And then we have all the values between negative 1 and 3, also up to and not including negative 1 and negative 3 respectively. And then again, we have all the values down to negative 3, but we do not include negative 3. So this interval is every single number except negative 1 and negative 3. But I want you to try one now. Find the domain of f of x is equal to 3 divided by the square root of x minus 1. Now here, you'll need to incorporate a little bit from the first example and a little bit from the second example. Be careful because the domain is a bit tricky on these types of problems. Keep in mind what the square root values you can take, and also keep in mind what you cannot divide by. All right, that's going to be it for today. I will see you all in the next lecture.